Hey, sleepers! Tonight, we're journeying into the quiet heart of a laboratory, where a tiny shimmering cloud holds a secret about the nature of time itself. Outside, the world spins at its usual pace. Cars move, clocks tick, seasons change. But here, in the deep chill of a quantum realm, something extraordinary is happening. A beam of light, the fastest thing in the universe, is being asked to wait. It enters a fog of atoms colder than deep space and slows to a gentle stroll. It's a place where the rules of our reality bend, and we get a glimpse of the universe's hidden machinery. So before you get comfortable, take a moment to like the video and subscribe. We'd also love for you to share your location and what time it is for you in the comments below. It's always wonderful to see where everyone is tuning in from, all connected in this one moment, ready to explore another. So close your eyes, take a deep breath, and get ready to drift off as we explore the experiment that stopped time. In 2019, this phrase began to appear in the quiet corners of the scientific world, a whisper that sounded like something from a dream. The experiment that stopped time. It feels like a title from an old storybook, a power that belongs to wizards or ancient gods. But this story does not take place in a mythical kingdom. It takes place in a laboratory, a place of stainless steel, humming machinery, and incredible precision. The scientists who performed this feat did not build a machine to travel to the past. They did not leap into the future. What they accomplished was more delicate, more subtle, and perhaps even more profound. They took a pulse of pure light, the fastest thing that exists, and they asked it to slow down. They convinced it to wait, not just a little bit slower, the way light slows when it passes through the water in a glass. They slowed it to a speed so incredibly leisurely that you could easily outpace it with a brisk walk. And in the most refined versions of these experiments, they brought the light to a complete and total stop, a full stop. And then, after a quiet moment passed, they released it. They let the light go, and it continued on its journey as if it had only paused to catch its breath. To begin to understand how such a thing is possible, we must first travel to a place of unimaginable cold. This is a cold that makes the most brutal Antarctic winter feel like a warm, sunny afternoon. We are on a journey toward the coldest temperature that can possibly exist. It is a fundamental limit of the universe. This temperature is known as absolute zero. On the Celsius scale we use for our weather, it is minus 273.15 degrees. It is so cold, scientists created a special scale just for it, a Kelvin scale. On the Kelvin scale, this ultimate cold is simply zero. 0 Kelvin. At this temperature, everything we think we know about the world begins to change. In our warm, everyday reality, atoms are like a huge crowd of very energetic dancers. They are all bouncing, spinning, and bumping into each other. This chaotic, energetic dance is what we feel as heat. The more the atoms dance, the hotter an object is. When you cool something down, you are essentially asking all those little dancers to calm down. They move less. They bump into each other less often. They become slow and sluggish. But something truly magical happens as you get closer and closer to absolute zero. The atoms do not just become sluggish. They begin to lose their sense of self. They begin to forget that they are individual dancers. This is where our story introduces a brilliant physicist from the early 20th century. His name was Satyendra Nath Bose, and he was working in British India. He was studying the new and very strange science of quantum mechanics. He was particularly interested in particles of light, which we now call photons. He came up with a completely new way to count them, a new kind of statistics for these quantum particles. He wrote down his ideas in a scientific paper. He sent it to the most prestigious journals of the time, but they rejected it. They didn't understand the importance of his work. It was too new, too strange. So, in a moment of brilliant and humble inspiration, Bose decided to go straight to the top. He mailed his paper directly to the most famous scientist on the planet, Albert Einstein. Einstein read Bose's paper and immediately saw the genius within it. He was so impressed that he personally translated the paper into German. He used his own reputation to make sure it was published. But Einstein did more than that. He realized that Bose's new mathematics could be applied not just to particles of light, but to atoms as well. And this led Einstein to a startling prediction. He predicted that if you could cool a group of certain kinds of atoms, called bosons in honor of Bose, down close enough to absolute zero, they would all collapse into the exact same quantum state. They would stop behaving like a crowd of individual atoms. They would start acting like one single, massive, collective entity, a kind of superatom. Let's try an analogy. Imagine a huge marching band practicing on a field. Before the director starts, everyone is doing their own thing. Some are talking, some are tuning their instruments, some are stretching. They are a collection of individuals. They are like warm atoms. But then the drum major blows the whistle. Suddenly, everyone snaps to attention. They all begin to march in perfect, synchronized lockstep. They move as one. They have a single, shared purpose and a single, shared identity. They have become a collective. This strange, predicted state of matter is called a Bose-Einstein condensate. For short, scientists call it a beak. For many decades, this was just a beautiful idea on a piece of paper. The technology to create the extreme cold needed to see it simply did not exist. It remained a theoretical dream for over 70 years. It was not until 1995 that two American physicists, Eric Cornell and Carl Wieman, working in their lab in Boulder, Colorado, finally succeeded. They created the very first Bose-Einstein condensate. It was a monumental achievement, a new state of matter created by human hands, and it earned them the Nobel Prize in Physics. Now, let's take a moment for a visualization. Imagine you could shrink down, smaller than a speck of dust, and enter the heart of one of these experiments. You find yourself floating inside a perfect vacuum chamber. The silence is absolute. The walls around you are a complex web of mirrors, lenses, and magnetic coils, all humming with a deep, silent energy. Suspended in the very center of this chamber, held in place by invisible magnetic fields, is a tiny, shimmering cloud. It is almost impossible to see. It looks like the faintest wisp of mist, far smaller than a single grain of sand. This is the Bose-Einstein condensate. The atoms inside this tiny cloud are almost perfectly still. They have been cooled to just a few billionths of a degree above absolute zero. They are colder than any natural place in the entire known universe. Colder than the dark, empty space between the galaxies. And all of these atoms are now marching in lockstep. They have overlapped, their identities have merged, and they have become one. This beautiful, fragile, and impossibly cold cloud is the stage for our experiment. It is the special, magical medium that will allow us to play our trick on light. It is the cosmic honey that will slow down the fastest thing in the universe. Now, let us introduce our guest of honor, light itself. What is light? This is a question that philosophers, artists, and scientists have wrestled with for thousands of years. We know it is what allows us to see the vibrant colors of the world. It is the gentle warmth of the sun on our skin. It is the fundamental energy that powers almost all life on Earth. In the language of physics, light is a form of electromagnetic radiation. It is a wave of pure energy, rippling through the fabric of space. But it is also something else. This is where the quantum world gets wonderfully strange. Albert Einstein helped us understand that light is also a particle. It comes in tiny, discrete packets of energy called photons. This is one of the first and most fundamental puzzles of quantum physics. Light is somehow both a wave and a particle at the exact same time. This is called wave-particle duality. It is like a coin that is both heads and tails simultaneously, until the moment you look at it. Depending on the experiment you design, light will reveal itself to you as a wave, or it will reveal itself as a particle. It is a shapeshifter. The most famous quality of light, of course, is its speed. When a photon is traveling through the perfect vacuum of empty space, it moves at a speed of approximately 299,792 kilometers per second. That is about 186,282 miles per second. This is the ultimate speed limit of the universe. Einstein's theories tell us that nothing with any mass can ever reach this speed, and nothing at all, with or without mass, can ever exceed it. This speed is so fundamental to the way the universe is built that it is woven into the very mathematics of reality. It is the C in the world's most famous equation, E equals mc. From our slow, human point of view, this speed is almost incomprehensible. It is practically instantaneous. A single photon could circle the entire Earth more than 7 times in the blink of an eye. The light from our sun has to travel for over 8 minutes across 150 million kilometers of empty space just to reach us. When you look up at the moon, you are not seeing the moon as it is right now. You are seeing it as it was about 1.3 seconds ago. That is how long it took for the light to travel from the moon to your eye. When we look at the closest star to our sun, Proxima Centauri, we are seeing a 4-year-old ghost. The light from the beautiful Andromeda galaxy, our nearest large galactic neighbor, has been on its journey for 2.5 million years before finally reaching our telescopes. But this cosmic speed limit, this C, only applies when light is traveling through a perfect vacuum. When light has to travel through a substance, through any kind of material, it slows down. Think of it like a champion runner. On a clear, open track, she can run at her absolute top speed. But imagine if her track was suddenly flooded with water up to her knees. She would slow down dramatically. The water molecules would get in her way. She has to push through them, interacting with them, and it slows her progress. It is very similar for a photon of light. When a photon enters a transparent material like water or glass, it begins to interact with the countless atoms inside that material. The photon is absorbed and then re-emitted by the electrons orbiting the atoms. This process of absorption and re-emission takes a tiny, tiny fraction of a second. But when this happens billions upon billions of times, as the light passes through the material, those tiny delays add up. The overall speed of the light pulse as it moves through the material is reduced. In water, for example, light slows down to about 75% of its vacuum speed. In a diamond, which is famous for the way it sparkles and plays with light, it slows down to less than half its top speed. This slowing of light is what causes the familiar phenomenon of refraction. It is why a straw in a glass of water looks like it is bent at the surface. So we have established that light can be slowed down. It happens all the time, all around us. But the slowing we see in everyday materials, like water or glass, is nothing. It is a tiny change compared to what we can achieve inside a Bose-Einstein condensate. The Beck is not just a very dense material. It is a quantum material. Its atoms are all acting in perfect unison. And this unified behavior allows for a very special kind of quantum trick. It is a trick that can take a cloud of atoms that should be completely dark and opaque and suddenly make it perfectly transparent. This remarkable trick is called electromagnetically induced transparency. Scientists often call it EIT for short. The name sounds very technical, but the core idea behind it is surprisingly simple and elegant. Let's imagine a single atom. This atom, like all atoms, can absorb light, but it is a very picky eater. It will only absorb or eat photons of a very specific color, which means a very specific energy or frequency. If you shine a laser of that exact frequency onto a cloud full of these atoms, they will all happily gobble up the light. The cloud will be completely opaque to that color of light. The light will not be able to pass through. It would be like trying to shine a flashlight through a black curtain. Now, here is the clever part. What if we could somehow change the atom's appetite? What if we could convince all of them, at the same time, that they are no longer interested in eating that specific color of light? This is precisely what IT does. We use a second laser beam. This is called the control laser. This control laser is tuned to a completely different frequency. When we shine this control laser onto our cloud of atoms, it puts all of them into a special, delicate quantum state, a state of superposition. In this special state, due to a clever phenomenon called quantum interference, the atoms are suddenly forbidden from absorbing our first laser beam. It is as if the control laser has broadcast a message to all the atoms at once, saying, "You are no longer allowed to eat that particular flavor of light. From now on, you must ignore it." So now, what happens? We have our cloud of atoms, which should be opaque. We have our control laser shining on it, putting it into this special state. Now we send in our original pulse of light, the very same light that the atoms would normally have absorbed instantly. But now, because of the control laser, the atoms ignore it. The light pulse passes straight through the cloud as if it were not even there. The opaque cloud has become crystal clear. It has become transparent. But here is the true magic. This is the heart of the experiment. In this state of induced transparency, something else happens to the light pulse. It is dramatically, profoundly slowed down. Why? Why does becoming transparent also mean becoming slow? The reason is that the light pulse isn't just ignoring the atoms. It is entering into a strange and intimate dance with them. The original light pulse and the control laser beam work together. They create a new kind of wave that propagates slowly through the synchronized atoms of the BE. This new wave is not purely light, and it is not purely an atomic state. It is a hybrid, a mixture of the two. Physicists call this strange hybrid a dark state polariton. The best way to think about it is that the light pulse imprints its information onto the collective state of the atoms. All the properties of the light pulse, its shape, its intensity, its phase, are transferred from the photons to the BEC. The atoms of the BA collectively remember what the light pulse looked like. The energy of the light pulse is now stored in the synchronized wiggle of the atoms. This wave of atomic wiggling then travels very, very slowly through the condensate. When this atomic wave reaches the far side of the cloud, the process reverses. The information that was stored in the atoms is converted back into a light pulse. A new photon is born, with all the exact same properties as the one that entered. This new photon then exits the cloud and continues on its journey at the normal speed of light. Let's try another analogy. Imagine you have a secret message written on a piece of paper. You need to get this message across a very crowded and noisy ballroom. If you just try to shout the message, it will get lost in the noise. The information will be corrupted. But what if you could teach everyone in the ballroom a special synchronized dance? You go to the person at the very front of the room, and you teach them the first move of the dance. They then teach it to the person behind them, who teaches it to the person behind them, and so on. The pattern of the dance moves like a slow wave across the room. The dance itself contains the information of your secret message. When the dance pattern finally reaches the person at the far end of the ballroom, they know the final move. They can then translate that dance back into the original message on the paper. The message didn't fly across the room at the speed of sound. Its information was carried slowly and carefully by the collective movement of the people in the room. This is very similar to what happens to the light in the beck. Its information is encoded onto the atoms. It is carried slowly across the superatom cloud, and then it is released. This entire process of encoding the information, carrying it, and then decoding it takes time. A lot of time, in quantum terms. And that is what we observe as the light pulse slowing down to a crawl. This astonishing technique was first brought to life by a brilliant Danish physicist named Lene Vestergaard Howe. In the late 1990s, she was leading a research team at Harvard University. In 1999, her team was the first to use a Bose-Einstein condensate and the EIT technique to slow a pulse of light down to just 17 meters per second. That is about 38 miles per hour, the speed of a car driving through a city. It was an incredible achievement that captured the imagination of the world. They had taken the universe's ultimate speedster and forced it to obey a city speed limit. A few years later, in 2001, Professor Howe and her team took the experiment to its logical and seemingly impossible conclusion. They sent a pulse of light into their ultra-cold atomic cloud. Then, while the light pulse was right in the middle of the cloud, transformed into that slow-moving atomic wave, they did something audacious. They suddenly turned off the control laser. Turning off the control laser broke the delicate quantum state. The pathway for the information to be converted back into light was now closed. The light pulse was trapped. It couldn't move forward. It couldn't turn back. It simply stopped. Its information was now fully and completely imprinted onto the stationary atoms of the beak. The light itself was gone. Its photons no longer existed. But its ghost, its soul, all of its quantum information was stored in the silent, frozen cloud of atoms. The cloud of matter had literally learned the light. For a brief period, they held it there in storage. Then they turned the control laser back on. The pathway was reopened. The stored atomic information was instantly converted back into a pulse of light. And out from the other side of the cloud came the light pulse, perfectly reformed, a perfect replica of the one that had entered. It then sped off again at its normal, blistering pace. They had stopped light, and then they had brought it back to life. The 2019 experiments, and the many others that have happened in labs around the world, are all built upon these incredible foundations laid by scientists like Bose, Einstein, and Howe. Researchers are constantly refining the techniques. They are using different types of atoms. They are finding ways to hold the light for longer periods of time. They are studying the intricate details of the process with ever-increasing precision. They are pushing the absolute limits of our ability to control the quantum world. So to recap our experiment, we begin with a tiny, ultra-cold cloud of atoms, a Bose-Einstein condensate. We use two carefully tuned laser beams. One is our probe beam, the pulse of light whose information we want to slow down and store. The other is our control beam, which creates the state of electromagnetically induced transparency. We send in our probe pulse. It slows to a crawl as its information is handed off to the synchronized atoms. And if we choose, we can switch off the control beam at just the right moment, trapping that information, holding the ghost of a light pulse in the heart of that tiny frozen cloud. Now we must face the most mind-bending question of all. What does any of this have to do with time? The headlines talk about stopping time, but we haven't built a time machine. The physicists in the laboratory did not stop aging. The clocks on the wall did not freeze. So why do we make this profound connection? The link is deep and subtle, and it leads us back, once again, to Albert Einstein and his revolutionary theories of relativity. Einstein taught us that space and time are not two separate, independent things. He showed that they are intricately woven together into a single, flexible, four-dimensional fabric that he called spacetime. He also showed us that this fabric can be bent and warped by the presence of mass and energy. This warping of spacetime is what we experience as gravity. But most importantly for our story tonight, he showed us that the experience of time is not absolute. It is relative. The rate at which time passes for you depends on how fast you are moving through space. The faster you travel through space, the slower you travel through time, relative to an observer who is standing still. This is not a philosophical idea or a metaphor. It is a hard physical fact of our universe, proven by countless experiments. The GPS satellites that orbit high above the Earth are moving at very high speeds. Because of this, the clocks on board those satellites actually run slightly slower than the clocks here on the ground. The difference is incredibly small, just a few microseconds per day. But if the engineers who designed the GPS system didn't account for this relativistic time-slowing effect, your phone's navigation would become inaccurate by several kilometers every single day. If you could board a futuristic spaceship and travel at 99.9% of the speed of light to a distant star and back, decades or even centuries might pass on Earth, while you would have only experienced a few years. Time would have passed much more slowly for you. And here we come to the ultimate limit of this effect. What about a particle of light, a photon, which travels at the full speed of light? For a photon, time does not pass at all. From the photon's own point of view, if we can even call it that, time is frozen. Its creation and its absorption, the start of its journey and the end of its journey, happen in the very same instant. A photon that travels from the sun to the Earth for 8 minutes experiences no time. A photon that travels from a distant galaxy for 1 billion years experiences no time. Its entire journey across the cosmos is, for it, instantaneous. Light, in its natural, untethered state, is timeless. It is the one entity in the universe that exists completely outside the forward flow of time as we perceive it. It is the absolute benchmark against which the passage of time is measured. So, when we take this timeless entity, light, and we force it to participate in our world of time, we are doing something profound. By slowing it down, by stopping it, we are performing an incredible act of manipulation. We are taking the master clock of the universe and forcing it to tick to our own rhythm. We are blurring the line that separates the timeless from the temporal. This is not about traveling through time. It is about seizing control of the flow of information at the most fundamental level possible. It is about manipulating the very thing, light, whose constant speed defines the relationship between space and time for everything else. Let's pause here for a moment. Take a slow, deep, and gentle breath. In your mind's eye, picture that beam of light. A pure, perfect pulse of energy traveling through the absolute emptiness of space. In its own frame of reference, it exists everywhere along its path at once. It experiences no before and no after. Its existence is a single timeless instant. Now, picture that pulse of light approaching the shimmering, ultra-cold cloud of the Bose-Einstein condensate. It enters this strange quantum fog, and suddenly its very nature is changed. Its information becomes bound to matter. It is forced to participate in a process. It has to be encoded. It has to be passed from atom to atom. It has to be decoded. For the first time in its existence, it is part of a sequence. It now has a before, which was entering the cloud. It has a during, when its information is held within the atomic dance. And it has an after, when it is finally released. We have taken a timeless being, and we have imposed a timeline upon it. We haven't stopped the flow of time in the room, but we have stopped a piece of light within time. It is a subtle distinction, but a profoundly beautiful one. What are the potential uses for this incredible new ability? What can we do with the power to stop and store light? The most immediate applications are not in the world of science fiction, but in the very real and developing world of technology, especially in the field of quantum computing. A normal classical computer, like the one in your phone or laptop, works with bits. A bit is a simple switch. It can either be off, which we call a 0, or it can be on, which we call a 1. A quantum computer, on the other hand, works with qubits. A qubit is a quantum bit. And thanks to the beautiful weirdness of quantum mechanics, a qubit can be a 0, a 1, or it can be both a 0 and a 1 at the exact same time. This state of being two things at once is called a superposition. This ability allows quantum computers to perform certain types of calculations millions of times faster than any classical computer could ever hope to. They could revolutionize medicine, materials science, and artificial intelligence. But building a working quantum computer is one of the greatest scientific challenges of our time. Qubits are incredibly fragile. The slightest vibration, the smallest change in temperature, the tiniest stray magnetic field from the outside world can disturb them and destroy their delicate quantum state, a process called decoherence. One of the biggest hurdles is creating a reliable quantum memory. How do you take the information from a qubit and store it safely without looking at it and destroying its superposition? This is where our stopped light experiment comes into play. Light, in the form of photons, is an excellent way to transmit quantum information over long distances. We can send it through fiber optic cables. But light is, by its very nature, a terrible way to store information. It is always on the move. You can't just tell a photon to sit still and wait. Atoms, on the other hand, are much better for storage. Using magnetic traps, we can hold them in place for long periods of time. They can be very stable. The process of stopping light in a Bose-Einstein condensate is the perfect bridge between these two worlds. It is a light-to-matter converter. We can take quantum information that is encoded in a pulse of light, transfer that information to the stable, stationary, and collective state of the atoms in the B key for safe storage, and then, whenever we need it, we can turn the control laser back on and release that information back into a new pulse of light. This could be a key component in building the quantum networks that will one day connect quantum computers together, creating a future quantum internet. This research also gives us a new window to peer into the fundamental nature of the quantum world itself. By studying the intricate details of the interaction between light and matter in these extreme, pristine conditions, we can test the predictions of quantum theory with a rigor that was never before possible. We can explore the mysterious and fuzzy boundary that separates the quantum world of individual atoms and photons from the classical world of our everyday experience. This is one of the deepest mysteries in all of science. Why does a single atom behave in such a strange, probabilistic, and ghostly way, while a huge collection of trillions upon trillions of atoms, like a bowling ball, behaves in a solid, predictable, classical way? Experiments like this one, which create a massive object, the BEC, that still behaves as a single quantum entity, sit right on that mysterious border. They help us to understand how our solid, predictable world emerges from the strange and fuzzy reality that lies beneath. There is a profound beauty in the pure, simple curiosity that drives this kind of research. The scientists who spend years, sometimes decades, in their windowless labs, meticulously aligning lasers and cooling atoms to temperatures colder than space, are not just trying to build a faster computer. They are driven by a deep, fundamental, and very human desire to understand. They are asking the biggest questions a person can ask. What is matter? What is light? What is time? What is the fundamental nature of reality itself? In many ways, they are like artists. But their canvas is the very fabric of space-time, and their paints are the fundamental forces and particles of the universe. Their work is a form of pure exploration, not of new continents or new planets, but of new states of being, new and exotic ways for reality to configure itself. And we should never forget the human element at the heart of this story. These incredible laboratories are not run by faceless, abstract thinking machines. They are run by people. People with extraordinary patience, with unwavering dedication, and with a childlike sense of wonder that they have never lost. Think of Satyendra Nath Bose in India, a physicist from a colonial nation, having the courage to challenge the scientific establishment and send his radical new idea to the most famous scientist in the world. Think of Lin Hao at Harvard, a woman leading a team in a field historically dominated by men, and achieving something that many of her peers believed to be impossible. The story of science is, and has always been, a profoundly human story. It is a story of collaboration, of building upon the work of those who came before, of standing on the shoulders of giants. And it is a story of those rare, magical moments of pure, unadulterated discovery, when the universe reveals a new secret to you. This is a global effort. Physicists in the United States, in Germany, in Austria, in China, in Japan, all over the world, are contributing small pieces to this grand and beautiful puzzle. They share their results openly. They critique and build upon each other's work. And together, as a species, they push the boundaries of our knowledge forward. The technology itself is a symphony of human ingenuity. To create a Bose-Einstein condensate, you must first create a near-perfect vacuum. You take a sealed chamber and you pump almost all the air out of it until the pressure inside is lower than the pressure on the surface of the moon. You have to do this to make sure that no stray, warm air molecules can bump into your precious, cold atoms and ruin the experiment by heating them up. Then you begin the cooling process. The first stage uses a complex and beautiful technique called laser cooling. This seems completely counterintuitive. How can you use a laser, which is a beam of concentrated light and energy, to make something colder? The trick is to tune the laser to a very specific color or frequency. The frequency is set to be just slightly lower than the frequency that the atoms naturally like to absorb. Now, an atom that is moving towards the laser beam will see the light's frequency as being slightly higher. This is due to the Doppler effect. It is the exact same reason an ambulance siren sounds higher pitched as it drives towards you and lower pitched as it drives away. This Doppler shift makes the laser light the perfect frequency for the approaching atom to absorb. But when the atom absorbs the photon from the laser, it gets a tiny kick backwards in the opposite direction of its motion. This kick slows the atom down. By setting up 6 laser beams pointing inwards from all 6 directions, up, down, left, right, front, and back, you can create a region in the center where atoms are constantly being bombarded by photons that slow them down, no matter which way they are moving. This creates a thick, soupy region that physicists poetically call optical molasses. The atoms become trapped as if they are trying to move through thick, cold honey. But even this incredible technique is not enough to get the atoms cold enough to form a messy. The final stage of cooling requires one last clever trick. This process is called evaporative cooling, and it is the very same principle that cools your hot cup of tea or coffee on a cold day. The hottest, most energetic water molecules have enough energy to break free from the surface and escape as steam. When they leave, they take their energy with them. This lowers the average energy, and therefore the average temperature, of the liquid left behind. In the lab, the physicists do something very similar with their laser-cooled atoms. They hold the cloud of atoms in an invisible bowl created by magnetic fields. Then, they very slowly and carefully lower the strength of the magnetic field. This is like lowering the sides of the bowl. The most energetic, hottest atoms now have enough energy to spill over the edge of the magnetic trap and escape. The ones that are left behind are, on average, colder. By continuing this process, precisely shaving off the hottest atoms over and over, they can bring the temperature of the remaining cloud down to just a few billionths of a degree above absolute zero. And at that magical point, suddenly, the phase transition occurs. The individual atoms vanish, and the Bose-Einstein condensate is born. A new state of matter, a quantum macro-object, materializes in the heart of the machine. It is a stunning testament to decades of theoretical work and experimental genius, all culminating in that one tiny, almost invisible shimmering cloud. Let us now think about the connection of all this to our own lives. It all seems so distant, so abstract. Ultra-cold atoms, quantum superpositions, dark-state polaritons, stopped light. What could this possibly have to do with the simple feeling of a cool breeze on your skin, or the taste of a fresh strawberry, or the sound of a familiar, comforting voice? In a direct, practical, everyday sense, perhaps not much, not right now at least. But in a deeper, more fundamental sense, it has everything to do with it. The very same universe that allows for the exotic existence of a Bose-Einstein condensate is the same universe that allows for our own existence. The fundamental laws of quantum mechanics that dictate the strange and beautiful behavior of those ultra-cold atoms are the very same laws that govern the atoms that make up our own bodies. The iron atoms in our blood that carry oxygen, the calcium atoms in our bones that give us structure, the carbon atoms that form the long, elegant chains of our DNA. All of these are collections of atoms, all obeying the same strange and wonderful quantum rules. This knowledge does not need to be complicated or intimidating. It can be a source of profound comfort and deep wonder. It can add a new layer of richness and beauty to the world we experience every day. The next time you look at a simple glass of water, and you see the way the light bends and sparkles as it passes through, you can think about how the speed of that light is being subtly altered by its constant interaction with trillions and trillions of individual water molecules. You can reflect on how that simple, common, everyday phenomenon is a distant cousin, a gentle echo of the extraordinary experiments that can bring light to a complete halt. The next time you stand outside and feel the warmth of a sunbeam on your face, you can think for a moment about the incredible journey those photons have just completed, traveling for 8 minutes across the vast, cold emptiness of space, existing in a state where time itself does not pass, only to end their timeless journey by delivering their energy to your skin, becoming a part of our world of warmth and time and sensation. This research is a powerful reminder that the reality we perceive is far stranger, more intricate, and more beautiful than it appears on the surface. We live our lives in what physicists call the classical world. It is a world of predictable causes and predictable effects. If you drop a glass, it will always fall down, not up. It will break. The sun will always rise in the east and set in the west. But underneath this solid, predictable, and comfortable surface lies the quantum world. A world of probability and potentiality, of waves and particles existing at once, of things being in many places at the same time until they are observed. Our familiar classical world is an emergent property of this deeper, stranger, quantum reality. Understanding that quantum world is like learning the fundamental grammar of the universe. It helps us to read the epic story that is written in the light of the stars, in the structure of matter, and in the very cells of our own bodies. There is a gentleness and a stillness to this kind of science. It is not about brute force. You cannot force a group of atoms to become a Bose-Einstein condensate by smashing them together. You have to coax them into it. You have to create an environment of almost perfect quiet, perfect stillness, and profound cold. You have to gently nudge and guide the atoms with precisely tuned and impossibly stable lasers. It is a science of incredible finesse and deep subtlety. It teaches us a quiet lesson that sometimes, to achieve the most extraordinary and powerful results, we do not need more force, but more peace, more stability. In the quietest, stillest, and coldest place on earth, we have learned how to have a conversation with light. Let your mind drift back one last time to that laboratory. It is late at night. The city outside is sleeping. The university building is dark and empty. But in one basement room, a soft light glows from a computer monitor. A small team of researchers, or perhaps a single graduate student, is watching the data come in. They are watching a tiny spike appear on a graph, a signal that tells them that they have once again succeeded. They have slowed light to a crawl. They have held it. They have released it. There is no loud cheer. There is no wild celebration. There is perhaps just a quiet, satisfied smile, a tired nod of accomplishment. It is a moment of deep and personal connection with the fabric of the universe. A moment where human curiosity and patience have gently peeled back one more layer of reality, revealing something beautiful, elegant, and strange that was hiding just beneath the surface. They have, for a fleeting, controlled moment, held the universe's swiftest messenger in their hands. They have looked into the timeless heart of light and gently asked it to wait for them. And in that quiet, frozen moment, they have touched the very edge of time itself. This knowledge does not give us power over time in the way a storybook might. It gives us a new and more profound perspective on it. It reminds us that our simple, human-centered view of a steady, linear now that marches ever forward is just one way of looking at things. For a photon, there is no now. There is only an instantaneous connection between its beginning and its end. For a supercooled atom in a Bose-Einstein condensate, there is a collective, unified state of being that is almost outside of time. Our reality is just one slice, one particular experience, in a universe of endless and wondrous complexity. And knowing this, truly feeling it, can be a profoundly peaceful thought. It can take some of the weight off our shoulders. We are all part of a grand, mysterious, and beautiful cosmic dance. We do not have to understand every single step. Sometimes it is enough just to be still, to listen, and to appreciate the music. The most striking finding, the one that catches the breath and sparks the imagination, is the sheer degree of the slowdown. The scientists took light, the universe's undisputed speed champion, and transformed it into something less than a pedestrian. In the vacuum of space, light travels at a speed that is difficult for the human mind to truly comprehend. It moves at nearly 300,000 kilometers in a single second. To put that into perspective, a beam of light could circle the entire Earth 7.5 times in the time it takes you to blink your eyes. It is a speed that defines the very structure of our reality, the ultimate speed limit that nothing else can ever reach. And yet, in these experiments, this cosmic sprinter was slowed to a speed of just a few meters per second. This is the pace of a brisk walk, or a leisurely bicycle ride. Imagine that for a moment. Imagine a beam of pure light, the essence of speed, moving so slowly through a tiny shimmering cloud that you could comfortably walk alongside it. You could watch it crawl from one side of the cloud to the other. This transformation is so extreme, so profound, that it feels like a violation of a natural law. It is like watching a cheetah, the fastest animal on land, suddenly decide to move with the patient, deliberate slowness of a tortoise. It is like seeing a lightning bolt hang in the air, a frozen river of electricity. The sheer scale of this change in speed is the first key finding, a testament to the incredible level of control that has been achieved over the fundamental interactions of our universe. It is a result that is both precisely measured and deeply poetic. This extraordinary control over the speed of light is the second major finding. The experiment is not a happy accident. It is not something that happens randomly. It is a demonstration of an exquisite and deliberate manipulation of the relationship between light and matter at the most fundamental level, the quantum level. The scientists are not just passive observers. They are active participants. They are conductors of a quantum orchestra. They use incredibly precise lasers, tuned to exact frequencies, to prepare the atoms in the supercooled cloud. They put these atoms into a very specific, very delicate quantum state. This state is what opens up a magical window of transparency, allowing the light to enter a medium that should, by all rights, be completely opaque. And it is this same carefully prepared state that forces the light to slow down. The physicists can turn this effect on and off at will. They can control the degree of the slowdown by adjusting the intensity of their control lasers. And most remarkably, they can stop the light pulse entirely, store its information within the collective consciousness of the atomic cloud, and then release it again, all with the flick of a laser switch. This is not just slowing light. This is catching it, holding it, and then letting it go. This level of control provides a powerful tool for future technologies. It suggests that we can build devices that use light and matter in ways we had previously only dreamed of, creating a bridge between the fast-moving world of photons and the more stable, storable world of atoms. This finding shows that the quantum world, for all its strangeness and probability, can be tamed. It can be engineered. The third key finding, and perhaps the most important for the future of physics, is what this experiment teaches us about a concept called quantum coherence. Coherence is a delicate and beautiful property of the quantum world. You can think of it like a perfectly trained choir. When all the singers in the choir are singing the exact same note, in perfect time, with the same volume and tone, they are coherent. Their individual voices merge into one powerful, pure, and unified sound. This is what a Bose-Einstein condensate is like. All the millions of atoms in that tiny cloud are behaving as one. They have lost their individuality and have entered a state of perfect, collective coherence. Now, imagine a single person in that choir starts to sing a different note, or sings out of time. The coherence is broken. The beautiful, unified sound becomes messy and noisy. In the quantum world, this loss of coherence is called decoherence, and it is the single biggest enemy of technologies like quantum computing. The slightest disturbance from the outside world, a stray magnetic field, a tiny vibration, a change in temperature, can destroy the fragile coherence of a quantum system, causing it to lose its quantumness and start behaving like a boring old classical object. What the slow light experiment demonstrates so beautifully is that we can perform complex operations on a highly coherent quantum system, like a BEC, without destroying its coherence. We can send a pulse of light into it. We can have that light interact intimately with all the atoms. We can transfer the light's information to the atoms. We can store it. We can then convert it back to light. And through this entire complex process, the delicate coherence of the BEC is maintained. The choir keeps singing its perfect unified note, even while it is performing this intricate dance with the light. This is a hugely important finding. It proves that quantum coherence is more robust than we might have thought. It shows that we can build complex quantum devices that can manipulate information without immediately falling apart. It gives scientists hope that we can build stable quantum memories and processors, the essential building blocks for a future quantum computer. In essence, this experiment is a beautiful demonstration of our growing ability to protect and preserve the magic of the quantum world while still putting it to work. It shows us that we are learning how to build with soap bubbles without popping them. These key findings, when taken together, paint a remarkable picture. We have found a way to slow the fastest thing in the universe to a human pace. We have demonstrated a level of control over the quantum world that allows us to catch and release light at will. And we have shown that we can do all of this while preserving the fragile, beautiful coherence that is the heart of quantum power. These are not just technical achievements. They are profound insights into the fundamental workings of reality. They open up new avenues for exploration and new possibilities for technology. They are the quiet, carefully measured results of decades of work, and they represent a new milestone in our long human journey to understand the cosmos and our place within it. Now, let us turn to the most captivating and perhaps most misunderstood aspect of this entire story, its connection to the idea of time manipulation. The phrase, "the experiment that stopped time," is powerful. It is evocative. It sounds like something pulled from the pages of science fiction. But what does it actually mean in the context of this real-world laboratory experiment? It is crucial to be very clear from the outset. The physicists who performed this experiment did not build a time machine. The clocks on the walls of the laboratory did not stop ticking. The researchers did not find themselves suddenly younger or older. The flow of time for us in our macroscopic everyday world was completely unaffected. So, if time itself was not stopped, why is this experiment so intimately linked with the concept of time? The connection is more subtle, more philosophical, and in many ways, more deeply rooted in the fundamental nature of physics. It is not about stopping time, but about manipulating the dynamics of time on a subatomic scale by controlling the universe's primary messenger, light. The link arises from the way we perceive and measure the passage of time. At its core, our understanding of time is built upon the transmission of information. An event happens, and we become aware of it when the information about that event reaches us. The primary carrier of this information, the fastest and most fundamental messenger in the universe, is light. When you see a lightning flash, and then a few seconds later you hear the thunder, you know the lightning happened first. The light from the flash reached you almost instantaneously, while the sound, traveling much more slowly, took several seconds. The speed of the information carrier determines your perception of the event's timing. Now, imagine a universe where you could control the speed of that information carrier. If you could slow down the light from a distant event, you would perceive that event as happening later than it actually did. You would be, in a very real sense, manipulating the temporal flow of information. You would be altering the when of that event from your perspective. This is the heart of the connection. By slowing light, by stopping it, we are taking control of the very fabric of how information travels through space-time. We are creating a situation where we can dictate the arrival time of a piece of information. On a tiny subatomic scale, within that little cloud of atoms, we are becoming the masters of a small piece of the timeline. To truly appreciate this, we must once again visit the strange and beautiful world of Albert Einstein's theories of relativity. Einstein's greatest revolution was to throw out the old, common-sense idea of time as a universal ticking clock that was the same for everyone, everywhere. He showed that time is not absolute. It is relative. The rate at which time passes for an observer depends on two things: their motion and the strength of the gravity they are experiencing. We have already touched on how moving at high speeds slows down the passage of time. This effect, known as time dilation, is a proven fact. Astronauts on the International Space Station, orbiting the Earth at high speed, age just a tiny fraction of a second slower than we do on the ground. It is a minuscule effect, but it is real and measurable. The stronger the gravity, the slower time passes as well. A clock at sea level will tick ever so slightly slower than a clock on top of a mountain, because it is in a slightly stronger gravitational field. These are not tricks of perception. They are real physical changes in the flow of time itself. Space-time, the four-dimensional fabric of our universe, is being stretched and compressed. Now let's consider the ultimate case, a particle of light, a photon. A photon travels at the maximum possible speed, the speed of light, c. According to the equations of relativity, for an entity traveling at speed c, the passage of time comes to a complete halt. From a photon's own perspective, its entire journey is instantaneous. A photon created in the core of the sun that travels for 8 minutes to reach your eye experiences 0 time. For that photon, its creation and its absorption by your retina happen at the same moment. A photon that travels for 13 billion years from the most distant galaxy we can see to the mirror of the James Webb Space Telescope also experiences no passage of time. Its epic journey across the cosmos, through evolving galaxies and expanding space, is for it an event that takes no time at all. Light, in its purest form, is timeless. It is an entity that exists outside the river of time that we are all carried along in. It is the fixed point, the absolute, against which all our relative experiences of time are measured. This is where the slow light experiment becomes so conceptually profound. It takes this timeless entity, the photon, and it forces it to have a temporal experience. By sending the photon into the Bose-Einstein condensate, we are binding it to matter. We are forcing its information to participate in a process that unfolds over time. The information must be encoded onto the atoms. It must propagate slowly through the cloud as a collective atomic wave, and then it must be decoded back into a photon. This process has a beginning, a middle, and an end. It has a duration. We have taken a piece of light, which should be timeless, and we have given it a history. We have stamped it with a before and an after. We have dragged it out of its timeless realm and forced it to participate in our world, the world of cause and effect, the world of passing moments. So, when we say we are manipulating time, this is what we mean. We are not building a machine to visit the dinosaurs. We are performing a far more subtle and fundamental act. We are manipulating the relationship between light, matter, and the relativistic nature of time itself. We are demonstrating that the timelessness of light is not an immutable law. It is a state that can be altered. We can intervene. We can take the master clock of the universe, and in a very small and controlled way, we can ask it to tick at a different rate. We can press pause. It is a manipulation not of the grand universal clock, but of a single tiny quantum pendulum. And by learning how to control that one pendulum, we learn more about the nature of the grand clock itself. Let's try a visualization to make this clearer. Imagine time as a great, flowing river. We are all in small boats, being carried along by the current. We cannot speed up or slow down our boats relative to the river's flow. Now, imagine that photons are like tiny, magical paper boats that instead of flowing with the river, can instantly teleport from any point on the river to any other point downstream. Their journey takes no time. Now, what the scientists have done is to create a small, calm, syrupy-thick eddy in the river. This eddy is the Bose-Einstein condensate. When one of these magical paper boats enters the eddy, it can no longer teleport. It gets caught in the thick, slow-moving syrup. It is forced to drift slowly from one side of the eddy to the other. Its journey now takes time. It has been forced to flow with the current, albeit a very slow one. The scientists have not stopped the river. They have just, for a moment, changed the nature of one of the boats, forcing it to experience the river's flow. This is the essence of the time manipulation at play. It is a change in the temporal experience of light itself. This ability has profound implications for how we think about information. In our classical world, information is robust. A book contains information, and that information stays there. But in the quantum world, information is delicate and tied to the physical system that carries it. A qubit in a quantum computer holds information, but that information is lost if the qubit is disturbed. Light is a great way to move quantum information around, but a terrible way to store it. Atoms are a great way to store quantum information, but a terrible way to move it over long distances. The slow light experiment provides the perfect translator between these two languages. It allows us to take the quantum information from a fast-moving photon and paste it onto a group of stationary atoms. We can store it, protect it, and then release it again when we are ready. We are, in effect, controlling the timeline of that piece of quantum information. We can decide when it arrives at its destination. We can create a quantum delay line, holding information in a buffer, a concept that is essential for any form of complex computation. This control over the when of quantum information is a form of temporal manipulation that is very real and has enormous potential for future technologies. It is the key to building the intricate timing circuits that a future quantum internet will require. So in the end, the connection to time manipulation is not about fantasy, but about a deeper understanding of physics. It is about recognizing that time is not a simple, monolithic concept. It is a complex, multifaceted property of our universe, deeply intertwined with space, matter, energy, and information. The experiment that stopped light did not stop time for us, but it did provide us with an unprecedented laboratory to study these interconnections. It gave us a new tool to probe the relationship between the timeless nature of light and the temporal world of matter. It allowed us to be, for the first time, not just observers of the flow of time, but active participants in the dynamics of a tiny corner of it. And in doing so, it has given us a new and more profound respect for the beautiful and mysterious nature of time itself. It reinforces the idea that our everyday experience is just one thin slice of a much richer and stranger reality. And it reminds us that by exploring these strange new realities in the lab, we learn more about the fundamental rules that govern our own. The experiment didn't stop time, but it certainly gave us a new reason to stop and think about time. The story of the 2019 experiments that so beautifully controlled the speed of light is not a story that appeared out of thin air. It is a single recent chapter in a much longer and richer narrative. Science rarely proceeds in giant, isolated leaps. It moves forward as a great, collaborative river, with countless streams of research and discovery flowing together over many years. To truly appreciate the significance of what was achieved in 2019, we must travel back in time ourselves, not in a machine, but through the pages of scientific history. We must understand the context, the foundation upon which these modern marvels were built. This work stands on the shoulders of giants, and one of the most important of those giants is the Danish physicist Lene Vestergaard Howe. In the late 1990s, the idea of slowing light to a crawl was still largely the stuff of theoretical speculation. Creating a Bose-Einstein condensate was itself a brand new Nobel Prize-winning achievement. The technology was at its absolute cutting edge. It was in this environment that Lene Howe, leading a team at Harvard University, embarked on a daring and ambitious project. Her goal was to use one of these new ultra-cold BECS as a medium to drastically slow down a pulse of light. In 1999, she and her team published a paper that sent shockwaves through the physics community. They had succeeded. They had sent a laser pulse into a sodium atom BEC and slowed it from its cosmic speed limit down to just 17 meters per second. That is about 38 miles per hour. They had taken the fastest thing in the universe and forced it to obey a city speed limit. It was an astonishing breakthrough. It was the first time this had ever been achieved, and it transformed the field of quantum optics overnight. It was the Wright brothers' moment for slow light. It proved that it was not just a theoretical possibility, but a practical reality. But Lin Hao was not finished. Her 1999 experiment was just the beginning. 2 years later, in 2001, her team published another, even more spectacular result. This was the paper that first truly demonstrated the idea of stopping light. They performed a similar experiment, sending a pulse of light into their bake, but this time, while the pulse was in the middle of the cloud, slowed to a crawl, they did something incredibly clever. They turned off the control laser that was creating the window of transparency. By doing this, they effectively trapped the light pulse. The information contained in the pulse was fully transferred to the atoms of the BEC, which entered a collective quantum state that was a perfect imprint of the original light. The light itself, the photons, had vanished, but its soul, all of its quantum information, was now stored in the cloud of matter. The atoms had learned the light. They held this information in storage for a fraction of a second, an eternity in the quantum world. Then they turned the control laser back on. In that instant, the process reversed. The stored atomic information was converted back into a pulse of light, and out from the other side of the cloud emerged a perfect replica of the original pulse, which then sped off at the normal speed of light as if nothing had happened. This was the first time that light had been brought to a complete standstill and then revived. It was a landmark achievement that laid the conceptual and experimental groundwork for all the slow and stopped light research that has followed, including the more refined experiments of 2019. Lin Hao's pioneering work established the fundamental techniques and demonstrated the incredible potential of this field. But the history goes back even further than that. The work of Lin Hao, and indeed the 2019 experiments, would have been impossible without several other key technological and theoretical developments that took place in the preceding decades. The entire field of quantum optics, the study of the quantum nature of light and its interaction with matter, relies on one crucial invention: the laser. Before the 1960s, the only light sources available were things like light bulbs or the sun. These sources are incoherent. The photons they produce are a jumbled mess, all with different frequencies, phases, and directions. They are like a noisy crowd of people, all shouting at once. A laser, on the other hand, produces coherent light. All the photons are perfect clones of each other. They have the same frequency, the same phase, and they all travel in the same direction. They are like a perfectly disciplined army marching in lockstep. This coherence is what allows for the precise control needed to manipulate quantum states. The invention of the first working laser in 1960 by Theodore Maiman, building on the theoretical work of physicists like Charles Townes and Arthur Shallow, was the necessary spark that ignited the entire field. Without the laser, there would be no laser cooling, no optical molasses, and no electromagnetically induced transparency. The next crucial piece of the historical puzzle was the development of the techniques to cool and trap atoms. Creating a Bose-Einstein condensate requires reaching temperatures just a hair's breadth above absolute zero. In the 1980s and 90s, this seemed like an impossible task. But a group of brilliant experimentalists developed a revolutionary set of tools to do just that. Physicists like Stephen Siechu, Claude Cohen-Tanuji, and William B. Phillips pioneered the techniques of laser cooling. They figured out how to use the tiny mechanical force exerted by photons to slow down atoms, creating the optical molasses we discussed earlier. They also refined the techniques of magnetic trapping and evaporative cooling. This body of work, for which they shared the 1997 Nobel Prize in Physics, was what finally gave scientists the ability to reach the ultra-low temperatures required to create a Beck. Their work built the refrigerator that was needed to cool the atoms down to the quantum regime. Without their contributions, the stage for the slow light experiment would have been empty. Finally, there is the theoretical history. A clever trick of electromagnetically induced transparency, or EIT, was not discovered by accident in a lab. It was first predicted theoretically in the late 1980s and early 1990s. Physicists, most notably a group led by Stephen E. Harris at Stanford University, were exploring the complex ways that multiple laser fields could interact with the quantum states of an atom. Through their calculations, they realized that it should be possible to create a special kind of quantum interference. This interference would cancel out the atom's ability to absorb light at a specific frequency, creating a narrow window of transparency. They also predicted that inside this window, the properties of the light would be dramatically altered, leading to a massive reduction in its speed. It was this theoretical prediction that inspired experimentalists like Lin Hao to try and see if it could be achieved in the real world. This is a classic example of the beautiful dance between theory and experiment that drives science forward. The theorists dream of what might be possible, and the experimentalists build the machines to see if the dream can be made real. So, when we look at the 2019 experiments, we see the culmination of this long and rich history. We see the legacy of Bose and Einstein's prediction of a new state of matter. We see the legacy of the invention of the laser. We see the legacy of the Nobel Prize-winning work on laser cooling and trapping. We see the legacy of the theoretical prediction of IT. And we see the legacy of Lin Hao's pioneering experiments that first turned all of this theory into a stunning reality. What has changed between 1999 and 2019? The answer is refinement, precision, and control. The lasers of today are vastly more stable and tunable than those of 20 years ago. The vacuum systems are better. The computer control systems are more sophisticated. The theoretical understanding of the process is deeper. This has allowed the researchers in 2019 and beyond to push the boundaries of the experiment. They can slow the light down even more. They can store it for longer periods of time, from microseconds to, in some recent experiments, even seconds. They can achieve higher fidelity, meaning the light that comes out is a more perfect replica of the light that went in. They are moving the technology from a proof of principle demonstration to a reliable and robust tool that can be used for other applications, like quantum computing. They are not just asking, can we do it? But how well can we do it? And what can we do with it? This historical context is important because it shows us that science is a human endeavor, built brick by brick over many generations. It is a story of countless individuals from diverse backgrounds, each adding their own piece to the puzzle. It is a story of theorists and experimentalists, of engineers and technicians, all working together. It reminds us that even the most revolutionary-sounding headline is part of a slow, steady, and collaborative march of progress. The experiment that stopped time in 2019 was not the work of a single moment, but the beautiful and resonant echo of a century of curiosity. Let us now turn our minds to the future. What does this incredible ability to slow and stop light truly mean for us? Where does this path lead? The implications of these experiments stretch out in many fascinating directions, from the very practical to the deeply profound. They touch upon the future of our technology, the way we communicate, and even our fundamental understanding of reality itself. The most exciting and perhaps most transformative potential application lies in the revolutionary field of quantum computing. We have spoken of this before, but it is worth exploring in greater, more gentle detail. A quantum computer is not just a faster version of the computer on your desk. It is a completely new kind of machine, one that operates on the strange and wonderful laws of the quantum world. Its power comes from its ability to hold multiple possibilities in its mind at once, a state we call superposition. This allows it to explore a vast landscape of potential solutions to a problem simultaneously, making it incredibly powerful for certain tasks, like designing new medicines, creating new materials, or breaking complex codes. However, this quantum power is built on a foundation of extreme fragility. The quantum bits, or qubits, that a quantum computer uses are like the most delicate of soap bubbles. The slightest touch from the outside world, a tiny vibration, a stray bit of heat, can cause them to pop, destroying the precious quantum information they hold. One of the greatest challenges in building a large-scale, useful quantum computer is finding a way to protect these qubits. And just as importantly, we need a way to communicate information between them reliably. A powerful computer is not just one processor. It is a network of processors, all talking to each other. How can we build a network for quantum computers? How can we send these fragile soap bubbles of information from one part of the machine to another, or even from one quantum computer to another across a city? This is where our stopped light experiment offers a beautiful solution. Light, in the form of individual photons, is an excellent messenger for quantum information. Photons travel at the ultimate speed, and they do not interact very much with their environment. So they can carry their quantum message over long distances through fiber optic cables without it being easily disturbed. They are the perfect high-speed mail carriers for the quantum world. But they have one major drawback. They are impossible to store. They are always on the move. You cannot tell a photon to just wait in a corner for a moment. This is a problem. In any complex computer, you need memory. You need buffers. You need places where information can be held and synchronized. You cannot have all the information arriving at the same time. You need a way to manage the traffic. The slow light experiment provides the missing piece of the puzzle. It acts as a perfect quantum mailbox. Imagine you have a quantum message encoded in a photon, our speedy mail carrier. You can send this photon into a Bose-Einstein condensate. Using the techniques we have discussed, you can slow the photon down and then stop it completely. The quantum message is now transferred from the fragile, fast-moving photon to the stable, stationary atoms of the Beck. The mail has been placed in the mailbox. The information is now held securely in the collective quantum state of the atomic cloud, which can be much more robust and long-lived than a single photon on the move. There it can wait, safe and sound. When the time is right, when the rest of the computer is ready for the message, you can flick the control laser back on. The mailbox opens. The atomic information is converted back into a brand new photon, an exact replica of the original, which then speeds off to its destination. This ability to store and retrieve quantum information on demand is a game changer. It is the key to creating a quantum memory, a technology that is absolutely essential for building a powerful quantum computer. It would allow us to synchronize the complex operations happening inside the machine. It would allow us to build quantum internet, a network that could connect quantum computers all over the world, allowing them to work together to solve problems far beyond the reach of any single machine. This is not just a small improvement. It is a fundamental building block. It is like inventing the memory chip for the classical computer. Without memory, a computer is just a calculator. With memory, it becomes a universal machine. The slow light experiment, in this context, is a critical step towards building a true, universal quantum computer. Let us take a moment to visualize this quantum internet. Imagine two cities, each with a powerful quantum computer working on a piece of a massive problem. They need to exchange information. They send messages to each other as pulses of light through a long fiber optic cable stretching between the cities. But the timing has to be perfect. The information has to arrive in the right order. At each end of the fiber, inside each quantum computer, there is a small, ultra-cold chamber containing a Bose-Einstein condensate. This is the quantum router. A pulse of light arrives from the distant city. It is guided into the BE and stopped. Its information is stored. The local computer can then perform some calculations. When it is ready, it retrieves the stored information and integrates it into its own process. This ability to buffer, to control the timing of the quantum data stream, is what would make such a complex, long-distance collaboration possible. It is a traffic control system for the information superhighway of the future. And the traffic cops are the quiet, supercooled atoms in a beak, patiently catching and releasing light. Beyond the far-reaching vision of quantum computing, there are also more immediate and practical implications in the world of classical telecommunications. The internet you are using right now, the global network that connects us all, is built on light. Trillions of pulses of light are flashing through a vast web of fiber optic cables every second, carrying emails, videos, and these very words. As our demand for data grows, we are constantly pushing these networks to their limits. We want faster speeds, more capacity, and fewer errors. One of the major challenges in building faster optical networks is managing the flow of data. Just like cars on a highway, if too many pulses of light arrive at a junction at the same time, you get a traffic jam. The data can get corrupted or lost. To prevent this, we need optical buffers and routers. We need devices that can temporarily store a pulse of light to let another one pass, and then release it back into the flow. Current technologies to do this are often inefficient. They usually involve converting the light pulse into an electronic signal, storing it electronically, and then converting it back into light. This process is slow, energy-intensive, and it can introduce noise and errors. Slow light offers a much more elegant solution. Imagine a tiny chip, a photonic integrated circuit, that has a small region dedicated to a slow light medium. When a data packet, a pulse of light, needs to be delayed, it can be routed into this region. Its speed is drastically reduced. It takes a much longer time to transit this small area. After the programmed delay, it emerges from the other side and rejoins the main data stream, perfectly synchronized. There is no need to convert it to an electronic signal. The information stays in the form of light the entire time. This could lead to all optical switches and routers that are much faster, more compact, and more energy efficient than what we have today. This could be a key technology for building the next generation of the Internet, allowing us to send more information more reliably than ever before. It would be a quiet revolution, happening inside the humming data centers that power our digital world, all thanks to a strange quantum effect discovered in a physics lab. Finally, we come to the most profound and perhaps most important implication of this work. It lies not in the technologies we can build, but in the understanding we can gain. Every great experiment is more than just answer a question. It opens up a dozen new ones. It gives us a new window through which to view the universe. The slow light experiment is a perfect example of this. It is a laboratory for fundamental physics, a tiny, controllable universe in a bottle. It allows us to probe the deep and mysterious relationship between light and matter with a level of clarity that was previously unimaginable. It is a place where two of the greatest theories of physics, quantum mechanics and relativity, meet and interact in a tangible way. Quantum mechanics governs the strange behavior of the atoms in the Big. Relativity governs the fundamental nature of the light. By watching them dance together in this controlled environment, we can learn more about the rules of the dance. We can test the predictions of quantum mechanics with incredible precision. Does the theory hold up in this strange new regime of a massive macroscopic object behaving as a single quantum entity? So far, the answer is a resounding yes, which is a powerful confirmation of our understanding. But physicists are always looking for the cracks. They are always pushing theories to their breaking point, because that is where new physics is discovered. The slow light experiment is a new tool to search for those cracks. It also provides a unique platform to study the nature of light itself. Is a photon that has been stopped and revived truly identical to the original? Does the process of imprinting its information onto matter, and then retrieving it, leave any subtle scars? Answering these questions can give us deeper insights into the nature of quantum information and the very definition of a particle. And of course, it brings us back to the nature of time. By showing that the temporal experience of light can be manipulated, it forces us to confront the question of what time truly is. Is time a fundamental property of the universe? A river that flows on its own accord? Or is it an emergent property, something that arises from the more fundamental interactions of particles and fields? This experiment does not answer that question, but it adds a fascinating new piece of evidence to the debate. It suggests that the relationship between events and the information that connects them is more pliable, more controllable than we ever thought possible. It deepens the mystery. It enriches the conversation. And for a scientist, a deeper mystery is often a far more valuable prize than a simple answer. The greatest implication of this work may simply be the wonder it inspires and the new questions it encourages us to ask. As we bask in the warm glow of these incredible possibilities, it is also important to anchor ourselves in the cool waters of reality. The journey from a beautiful laboratory experiment to a world-changing technology is often long, difficult, and filled with challenges. The slow light experiment, for all its profound beauty, is no exception. It is crucial to understand the limitations and hurdles that stand between what has been achieved in a lab and what might one day be possible in the real world. Acknowledging these challenges does not diminish the achievement. On the contrary, it gives us a deeper appreciation for the ingenuity and persistence that will be required to move forward. The first and most significant limitation is the sheer extremity of the conditions required. A Bose-Einstein condensate does not exist in nature. It is one of the most artificial states of matter ever created. To make one, you need to create an environment that is colder than any natural place in the known universe. We are talking about temperatures of just a few billionths of a degree, above absolute zero. Achieving this requires a room full of complex and expensive equipment. It requires powerful and precisely tuned lasers. It requires a near-perfect vacuum chamber, better than the vacuum of deep space. It requires cryogenic cooling systems with liquid helium. The entire apparatus is large, delicate, and consumes a great deal of energy. It is the very opposite of something you can carry around in your pocket. Let's try a visualization to really feel this challenge. Imagine you are an artist who has learned how to sculpt the most beautiful and intricate figures out of ice. Your sculptures are breathtaking, but there is a catch. You can only create and maintain these sculptures inside a special, super-powered freezer that takes up your entire house and costs a fortune to run. The moment you try to take your sculpture outside into the warm, sunny world, it instantly melts into a puddle. This is the challenge facing slow light technology. The beautiful quantum effect, our ice sculpture, can only exist in the deep freezer of the physics lab. The warm, noisy, chaotic world outside is like a summer day that would instantly melt the delicate coherence of the BEC. So, while this is a perfect tool for fundamental research in a controlled environment, it is a very long way from being a practical component in a laptop or a mobile phone. The first great hurdle is a problem of temperature. The second challenge, which we have touched upon but must state clearly, is to be precise about what this experiment does and does not do. It is a limitation of interpretation. Slowing a pulse of light is not the same thing as altering the flow of time itself. This is a crucial distinction. The headlines can be exciting, but they can also be misleading. The experiment did not create a time machine. The physicist who turns the knob on the laser does not suddenly see the world around them slow down. Their own personal clock, and the clock on the laboratory wall, continues to tick forward at its normal, relentless pace. The laws of causality, the idea that a cause must always precede its effect, remain firmly intact. You cannot use this technology to send a message back to yesterday to warn yourself not to eat that questionable burrito for lunch. It's a fun thought, but it is not what the physics allows. The manipulation is happening to the light pulse, not to the fabric of space-time in the room. Think of it like this. Imagine a movie playing on a screen. The movie has its own timeline, its own sequence of events. You, as the viewer, have a remote control. You can press pause. The movie stops. You have manipulated the timeline of the film. But you, sitting on your couch, continue to live and breathe. Your own time has not paused. The slow light experiment is like pressing pause on the movie of a single light pulse. The universe, the grand audience, continues on, completely unaffected. The intrigue and the power of the experiment lie not in the fantasy of time travel, but in the real physical marvel of being able to control a fundamental aspect of light's behavior. The limitation is that this control is local and specific. It does not grant us godlike power over the universal clock. It gives us a very specific and fascinating new tool. The third major set of challenges falls under the umbrella of scalability and real-world implementation. Even if we could overcome the temperature problem, there are other engineering hurdles to leap. One of the most significant is the issue of bandwidth. The special quantum state that allows for slow light, the light window, is typically very narrow. This means that the effect only works for light of a very specific color, a very narrow range of frequencies. It is like having a magical traffic light that can only stop red cars, but is completely blind to blue, green, and yellow cars. Real-world data signals, like those used in fiber optic communications, are not a single pure color. They are made up of a broad range of frequencies. To be truly useful as an optical buffer, a slow light device would need to be able to slow down a wide bandwidth of light, not just one specific shade. This is a major area of ongoing research, with scientists exploring different types of atoms and different techniques to try and broaden this operational window. Another challenge is fidelity. How perfect is the replica? When the light pulse is stored in the atoms and then retrieved, is the new pulse an absolutely identical twin of the original? Or is it more like a slightly blurry photocopy? In the current experiments, some of the information is always lost. The fidelity is not 100%. For some applications, like a simple optical delay, this might be acceptable. But for something as demanding as quantum computing, where a single error can ruin a whole calculation, you need near-perfect fidelity. You need to be able to store and retrieve your delicate quantum soap bubble without it being distorted in any way. Improving this fidelity, getting it as close as possible to 100%, is another key challenge that requires even greater control over the quantum states of the atoms. Finally, there is the challenge of miniaturization. To move this technology from the lab bench to a silicon chip, you need to shrink a room-sized experiment down to the size of a fingernail. This field, known as chip-scale atomic physics, is one of the most exciting frontiers in engineering. Researchers are developing incredible techniques to create tiny vacuum chambers, miniature laser systems, and magnetic traps, all integrated onto a single microchip. They are making progress, but the challenge is immense. It is like trying to build a perfect miniature Swiss watch, but all the components are individual, unruly atoms that you have to control with lasers. These limitations, the extreme conditions, the misinterpretation of time travel, and the immense engineering challenges of scalability are not reasons for despair. They are the roadmap for future research. They are the mountains that the next generation of scientists and engineers will set out to climb. Each challenge is an opportunity for innovation, and the history of science has shown us time and again that today's insurmountable hurdle is often tomorrow's solved problem. The impact of a great scientific discovery often ripples outwards, far beyond its specific findings or potential applications. It can change the way we think. It can reshape our understanding of a whole field of knowledge. The experiment that stopped time is one such discovery. Its broader impact on the world of physics is subtle, yet profound. It is deepening our understanding of the universe at its most fundamental level. It is forcing us to confront some of the oldest and deepest questions in science, and it is sparking the imagination of researchers, pointing the way towards new and exciting avenues of exploration. Its greatest legacy may not be a quantum computer or a faster internet, but a richer and more complete picture of reality itself. At its very core, this work has fundamentally deepened our understanding of the intricate dance between light and matter. This interaction is at the heart of almost everything we experience. It is why the sky is blue. It is why a leaf is green. It is how our eyes see the world. For centuries, we have studied this interaction, but we have always studied it in motion. We have been like biologists trying to understand how a hummingbird flies by watching it in real time. It is all a blur of motion, too fast to comprehend fully. What the slow light experiment gives us is a revolutionary new tool, a super slow motion camera for the quantum world. By slowing the process down, by stopping it mid-flight, we can for the first time see the individual steps of the dance. We can watch with incredible clarity how the information from a photon is absorbed by an atom. We can see how that information is shared and stored in a collective of atoms. We can witness the process of that information being converted back into a new photon. We are no longer just watching the blur. We are seeing every flap of the hummingbird's wings. This slow-motion view allows physicists to test their theories with unprecedented accuracy. They can measure the subtle properties of quantum coherence with new precision. They can study the exact dynamics of quantum state transfer. This detailed information is like gold for theoretical physicists. It allows them to refine their models, to patch up any small holes in their theories, and to gain confidence in their understanding of the quantum world. Every time a new experimental regime is opened up, it puts our existing theories to the test. So far, quantum mechanics has passed the test of slow light with flying colors. But science is always about pushing the boundaries. By studying this interaction in ever more detail, we might one day find a tiny discrepancy, a small anomaly where the experiment does not quite match the theory. And it is in these tiny cracks that new physics and new revolutions in understanding are often born. This experiment has given us a new and more powerful magnifying glass to search for those cracks. This research also has a profound impact on the ongoing conversation about the very nature of time. This is one of the oldest and most difficult questions in all of philosophy and science. Is time a fundamental feature of the universe, like space? Or is it an illusion, an emergent property that arises from a deeper, timeless reality? Is it a smooth, continuous flow? Or is it made of tiny, discrete ticks, like the frames of a movie? Physics does not have a final answer to these questions. In fact, our two greatest theories of the universe treat time in completely different ways. In Einstein's theory of general relativity, which describes gravity and the cosmos, time is a dimension, woven together with space into the fabric of space-time. It is dynamic and relative. In quantum mechanics, which describes the world of atoms and particles, time is treated very differently. It is more like a universal external clock, a background parameter against which quantum events unfold. This deep incompatibility in the way our two best theories treat time is a huge problem. It is one of the main reasons it is so difficult to unite them into a single theory of everything. The slow light experiment sits right at the fascinating intersection of these two worlds. It involves light, whose behavior is governed by relativity, and it involves the quantum states of atoms, which are governed by quantum mechanics. It is an experiment where these two different conceptions of time are forced to interact. While it does not solve the problem of time, it provides a new experimental arena in which to study it. By demonstrating that the temporal experience of a photon can be manipulated by a quantum system, it provides a tangible link between the two descriptions. It adds a new, intriguing data point to the grand debate. It encourages physicists working on quantum gravity and fundamental theory to think in new ways. It is a catalyst for conversation, a bridge between two different theoretical continents. And in science, conversation and the cross-pollination of ideas is often the seed of the next great breakthrough. Finally, the broader impact of this work is measured in the currency of inspiration. Science moves forward, not just on data and equations, but on curiosity, imagination, and the courage to ask, what if? A beautiful and mind-bending experiment like this one acts as a powerful beacon. It captures the imagination of not only the public, but also of young students who are just beginning their journey into science. It shows them that the world is still full of mystery and wonder, that there are still incredible discoveries waiting to be made. It can inspire them to pursue a career in physics, to become one of the people who will build upon this work in the future. It also sparks the imagination of other scientists. When one group of researchers shows that they can control something that was previously thought to be uncontrollable, it emboldens others. It creates a ripple effect of creativity throughout the scientific community. Other physicists will look at this result and ask new questions. If we can slow down light, what else can we slow down? Can we use similar techniques to control other types of waves, like sound waves or spin waves, in a magnetic material? Can we create a Bose-Einstein condensate of molecules, not just atoms, and store even more complex information? Could we ever dream of manipulating even more exotic entities, like neutrinos, or even the faint ripples in space-time known as gravitational waves? These may seem like wild and futuristic ideas today, but the slow light experiment makes it okay to ask them. It expands the boundaries of what we consider possible. It is not an endpoint. It is a beginning. It is a doorway that has been opened into a strange and beautiful new room in the vast mansion of physics. And scientists, filled with a fresh sense of wonder, are just now beginning to step across the threshold to explore what lies inside.